Hello everyone and welcome to this MIST seminar, which is the last MIST seminar of this academic year. And we're ending with a terrific talk by Graziella on soft X-ray imaging of geospace with SMILL. For those who don't know, Graziella is kind of the European lead of this SMILL mission, which is a collaboration between ESA and the Chinese Academy of Sciences, and promises to unlock a lot of new science and new views of the magnetosphere. And so I'm very excited to hear all about that. Take it away, Graziella.
Thank you very much, John, for the introduction. And welcome, everybody. I'm very glad to be able to describe SMILL to you and where we are with it. Now, SMILL offers a new global way to explore the relationship between the solar wind and the Earth magnetosphere. As you heard from John, it's a joint space mission between the European Space Agency and the Chinese Academy of Sciences, from beginning to end, really. And it's under development and is due for launch in 2024. Of course, I talk on behalf of many scientists and engineers in institutes and countries over the world that make up the SMILL collaboration. So now a quick outline of SMILL, the Solar Wind Magnetosphere Ionosphere Link Explorer. And it's a long acronym, but that's exactly what it's going to do. So it will investigate the dynamic response of the Earth magnetosphere to the impact of the solar wind in a way that is global and has never been tried before. So imagine a CME which is moving out of the sun, traveling interplanetary space, and hitting the Earth magnetosphere. And for favorable conditions of the orientation of magnetic field in the solar wind and the magnetic field of the Earth, we have penetration of solar wind particles in the magnetosheath. And now we know that there we have the production of soft X-rays by the process of charge exchange, which I'll talk a bit more later. And so SMILL will carry a soft X-ray imager that will map this radiation. Now, the particles that produce it eventually follow the magnetic field lines and precipitate down the poles of the Earth, causing the aurorae. So SMILL also carries a UV imager that will continuously monitor the northern aurora, as you can see in this diagram. In addition to that, SMILL also carries a package of in situ instruments that will measure the plasma conditions in the solar wind and in the magnetosheath. And it will do all of this from a very elliptical orbit, which you see outlined there, that takes it out to something like 19 Earth radii over the northern hemisphere. So now, having given this overview of the mission, now let's see what the scientific motivations for it are. And really, we want to study the full chain of events that drive the interactions of the solar wind and the Earth. And basically, the structure, the dynamics of the magnetosphere, we know are mainly controlled by magnetic reconnection that takes place between the solar wind and the magnetosphere and allows particles of the solar wind to penetrate it. And the basic theory of magnetospheric circulation is fairly well known, and it is illustrated by the cartoon at the top of my slide showing the progression of the Danji cycle. And we know that pretty well because it's been explored by many measurements, by in situ measurements by spacecraft, really many cases of spacecraft flying in geospace space, but they have investigated the situation on the micro scale. And the interaction is actually complex and takes place on a scale that is global. And so all of this is still not completely well understood, and also how that evolves with time. So that's where SMILL can give us more information. So SMILL can answer questions that will help us to distinguish the various ways in which this interaction takes place. And for instance, the character of the reconnection phenomenon, and also what triggers geomagnetic substorms and storms that are driven by the arrival of CMEs. And so essentially, SMILL will try and answer the question of what drives really space weather, which is so relevant nowadays to our technological infrastructure, both in space and on the ground. So here I have a couple of slides that focus on particular questions that we want to address. One is, what are the fundamental modes of the interaction on the day side of the solar wind and the magnetosphere? And in particular, when we talk about reconnection, when, under what conditions and where does it look to be steady or transient or bursty? What kind of morphology has it got? Is it patchy or global? And what on what do these characters depend? Are they the solar wind parameters like the beta parameter? Or are these characteristics depending on instabilities? And do the instabilities, are they cause or consequence of the phenomenon of reconnection? And is this reconnection happening on the equatorial level component, or is antiparallel at high latitude? And what determines that? What conditions lead to that? And what is the role of the magnetospheric cusps as well in this coupling of the solar wind and magnetosphere? And to illustrate what can happen in terms of cusp behavior, I have here 3 plots. I'd like you to concentrate on the top and the bottom ones. These are spectrograms where on the vertical axis we have the energy of ions measured by the cluster spacecraft, and the horizontal axis is essentially latitude and on the Earth. And what happens in the top spectrogram is at the time when cluster 4 was crossing the cusp with the interplanetary magnetic field IMF southward. And the bottom one is cluster 3, some 10 minutes later crossed the cusp, but by then the IMF had turned northward. And so we see directly what these different conditions of the magnetic field actually imply. And in practice, the ion energy decreases towards the pole for IMF southward at the top plot, and vice versa at the bottom, where the IMF has turned northward. And also we notice that the cusp expands poleward after this north turning of the field. I mean, this is one observation. What we hope to do with SMILL is actually to be able to follow this kind of behavior many more times in a more systematic way. Other questions that we want to answer are such like, what defines the substorm cycle? What triggers it? Now, we know that the auroral oval responds to changes in the conditions of the magnetosphere. so the question is, what triggers substorms? Is it the IMF orientation? Is it dynamic pressure? Are there seasonal effects? And it's interesting to see the diagram on the right-hand side that illustrates over a period of about 10 days of the plots, the diagrams you see at the bottom, how the auroral oval, especially the size of it, the radius of the oval, changes depending on the conditions of the solar wind incoming. So at the top, we have two images from the image spacecraft of the aurora that correspond on the left to a time of activity of the solar wind, the substorm, and at the right-hand side instead is a quiescent type of conditions in the magnetosphere. And we know that that was the case because we can look at the SIMH index in the central plot and the cross-polar cap potential at the bottom that clearly indicate there are at least two strong cases of substorm in this period. And so the top diagram showing the oval radius shows how the size of the aurora changed over this time. It's interesting to notice in terms of what SMILE will do is that there are lots of gaps in that timeline of the oval radius as measured by image, which had a orbital period shorter than SMILE. SMILE will have something like 40 hours of operations available continuously for UVI and SXI. And so we will be able to have this kind of timelines, but much more consequential, much more continuous than image provided. And then there are other modes of magnetospheric behavior that we are interested in studying, like sawtooth events or auroral beads. This is an area that the UVI will be very strong on. And then, and of course, the interesting thing is to make the connection between what UVI sees and what SXI has seen as the solar wind coming in from outside. And then the other question is, how do CME-driven storms arise? How are they related to substorms? And now we know that for long intervals of south IMF and when there is fast solar wind, that leads to enhanced reconnection. And so then the question is, though, is just the solar wind driving the only trigger for the storm, or are there any other triggers that we can identify? And also, what's the relation between a storm and a geomagnetic substorm? How do the storms end? These are all questions that have a very strong relevance to space weather. Now, there is an interlude here that relates to astrophysics and atomic physics, and that is what's new with SMILE is the use of solar wind charge exchange to observe image geospace. And so I say a word about charge exchange, this process that was known from the dawn of atomic physics, but only came on the forefront of astrophysics when comets were discovered to be strong soft X-ray sources. And it was understood that they are so because they travel through the solar wind and they are bright because of the production of soft X-rays by charge exchange. Okay, so solar wind charge exchange happens when you have a highly charged ion of the solar wind, like you see here on the left panel, a solar wind ion of oxygen 7+, and that interacts with an atom of hydrogen in the exosphere of the Earth, acquires an electron, and then is left in an excited state from which it decays with the emission of a soft X-rays, which for this particular transition is about half of a keV. And of course, this is just an illustration for one species of ions, but there are lots of other minor ions contained in the solar wind. They all produce different lines, different emission lines, depending on their atomic state. So the emissivity in the soft X-rays is expressed by the equation that you see there, where we see that is proportional to the density of the solar wind, the density of the neutrals, and G is the relative velocity of the two. And this proportionality is through a parameter alpha, which represents all the atomic physics that go into it. So like the cross sections for these charge exchange, and also the elemental abundances of the solar wind. So the X-ray emission is proportional to the density of the solar wind ions, the neutrals, and so as a consequence will be brightest in the Earth's dayside magnetosheath and the cusps. And I take you now a little bit back in the history of all of this and of how such thing as an unwanted variable soft X-ray background that we were seeing in X-ray observations of cosmic X-ray sources actually turns into a useful tool. So we go back to Rosat in the 90s, and it was Rosat that identified that comets are bright sources of soft X-rays. And also, he pointed out, you see the image on the right-hand side of the moon. That image shows us that apart from the illuminated side of the moon by the solar X-rays, which are scattered away from it, there is a residual amount of soft X-rays that come from the dark side of the moon. And that was a bit of a puzzle for some time until it was realized it's again a soft X-rays produced by charge exchange. In that particular case was because the line of sight to the moon by Rosat was going through the magnetosheath or the cusp. And so the produced solar wind charge exchange X-rays there were actually being picked up as projected on the dark side. And a similar phenomenon was seen by Suzaku when observing the north ecliptic pole. And again, as is illustrated in the diagram at the center, you have the line of sight that goes through the cusps or through the magnetosheath, and you have variable soft X-ray background affecting your cosmic observations. Now, all of this was studied in great detail by Jenny Carter, who did, and collaborators who did a survey of many XMM Newton observations that showed this variable background in the soft X-rays, and they demonstrated that this corresponds to variability in the solar wind, and also identify the arrival of a CME through this variable background, and demonstrated how the spectrum as well is made up of charge exchange lines, emission lines. Now, so the concept was generated that perhaps these X-rays from the magnetosphere, well, we could dismiss them as noise, but rather take them as a possible diagnostic tool, an imaging diagnostic tool of geospace. And so there were some early concept missions that were proposed in order to do exactly that, to use that magnetosheath emission and cusp emission to study the conditions of the magnetosphere and under the solar wind. And so MAGX and STORM were proposed to NASA, Axiom and Axiom-C to ESA. And, but these were, it was perhaps a bit too early. You see, it needed some convincing that X-rays are worth to be used as diagnostics of the interaction. And so what a prototype really of all of these was realized when we had, where there were two rocket flights. And all of these that demonstrated this possibility. Now, all of these missions I mentioned, and in fact, from there on, have been using the technology of lobster eye optic to focus the X-rays, because it allows large field of view with low mass. And that's how these two rocket flights carrying a soft X-ray imager were realized. And the concept matured substantially with time, and eventually SMILE was proposed for this joint ESA-CAS mission. It was chosen in 2015, selected for implementation, and then adopted into the ESA Cosmic Vision program in 2019. And now, as I said, the launch is expected at the end of 2024. Now, I want to stress that actually this is really a good beginning. And in fact, this idea of X-ray imaging of geospace is becoming very popular, And there are a number of missions that are now under development or under study. And so the first one to go, in fact, will be Cupid. This is a CubeSat with Brian Walsh, PI from Boston University. And this CubeSat, carrying a similar imager to the one that went on the rocket flights, will look up at the cusps from below and is due for launch at the end of this year. Now, Brian Walsh also is the PI of Lexi, a similar type of imager that is going to be deployed on the moon in one of the first landings within the NASA Artemis program. Then there is the STORM mission, a much larger mission with David Seibeck, PI, and that is in study phase and has been selected through competition, of course, for the NASA Heliospheric Explorer program. It's under study with another two competitors, but seems to have a good chance. Now, there's an extended version of the SMILE team that proposed the mission, actually wrote a white paper for the ESA Voyage 2050 call last year. And the idea there is exploring solar terrestrial interactions with multiple observers. The idea there is like a second generation SMILE with a larger payload, more remote imaging, and of two spacecraft that would look at both aurorae on Earth simultaneously to learn more of the solar wind impact. An idea has been proposed for the ESA a European lander logistic idea of landing instrumentation on the moon. And in that case, we called it X-ray monitor on solar impact on geospace from the moon. But that's, of course, at the level of an idea so far. And then actually there are two more missions under development in Japan and in China. So really we are progressing well in this imaging in X-rays, planetary conditions. And of course, we shouldn't forget that we have Bepi Colombo and its NIXIS X-ray telescope from Leicester University flying to Mercury. So good time for X-ray, planetary X-ray astronomers. Now I'll say a few words about the payload of SMILE, starting with the soft X-ray imager. Now, the only way to focus X-rays is really by grazing incidence. That's what is illustrated in the diagram at the top. And using lobster eye micropore optic, we can have a very compact camera. And you see a CAD image over here. And this type of technology allows us an ultra-wide field of view. The SXI has a field of view of 16 by 26 degrees. And it makes it the focusing by lobster eye technique makes the camera very compact with a focal length of 30 centimeter. And as I said, the mass is very low, and the whole instrument weighs some 36, some 40 kilograms. Over here on the left, we see a CAD image of the whole imager. And so the camera is the brown structure here. The dark structure over it is the baffle, which protects it from scattered sunlight and light from the bright Earth. Now, the detectors are CCDs, two large format CCDs. And above them, there is a radiation shutter that is shown in turquoise color in the structure there. And that is like a door that closes over the CCDs every time we come through the radiation belts to protect the chips. The CCDs will produce images as well as spectra, and we see examples of them at the bottom of the slide. And the spectra, at the top, you see a theoretical model of the solar wind charge exchange spectrum, which is in practice a simple overposition of many, many, many emission lines. And you see the response of the instrument convolved with the spectrum there. And we still can resolve the most abundant species of ions in the spectrum. And the PI of SXI is Steve from the University of Leicester. Here is some current image of where we are with the instrument. So far, we have the structural thermal model built of SXI, and you see on the left the primary structure of the telescope in this gold color. At the center is an exploded view of the whole telescope, and on the right-hand side, we see one of the large format CCDs. They are 8 centimeters square. So it's a real large X-ray CCD that we are using. We have 2 of them on board on the focal plane. They are made by Teledyne E2V. And in this case, you see it mounted in a test camera at the Open University. And there are ongoing tests on them, as well as there are ongoing, or there have been tests on the STM, the structural thermal model of the whole telescope, which you see here located on the vibration plate at the RAL testing facility. And this time you see the primary structure of SXI with the baffle mounted on top. Now, there is a very nice movie of a test, a vibration test that has been done on SXI STM. And that is the one listed there is the URL for the video. Unfortunately, I tried to show it in another talk I gave a couple of days ago. And because the vibration is so rapid, the connection speed of Zoom is actually making it much slower, and it does not offer the real feeling. And also, I didn't manage to get the noise because the video comes with noise. So I believe that John has put this link in the chat so that you can all have a look and be quite shaken by it. Okay, that was quite an interesting, a bit frightening experience to look at but all went well, so that's good. Okay, so now instead I have here a video which I hope should work. And this is an MHD simulation of what the X-ray emissivity predicted would be for the St. Patrick's Day storm in the year 2015. And in practice, Tianran, our collaborator in China, oops, now let's see if I can do, okay, I got it. She took the actual measured, I hope this is going to work, my cursor. Ah, good. Okay, she took the actual solar wind conditions measured at the time to predict the X-ray emissivity that it probably was produced in the magnetosheath and in the cusp, and SMILL would have seen, the SXI would have captured if it had been flying at the time. Of course, this is covering something like 10 hours, 15 hours, and is a bit of an accelerated version of what SMILL would have seen in the 20-second or 10-second that I've shown the video. But this is the kind of output that we are expecting to provide once we have the images that SXI will provide from flight. And of course, from the images, we'll be able to make up videos as I have shown. Now, what the video showed was the emissivity. So what is actually produced by simulating the MHD with the MHD model. Now, how do we get to simulating count maps, what we can expect from SMILL? Well, what we do is we take the modeled X-ray emissivity cube. You see an example here. So the MHD provided X-ray emissivity in 3 dimensions. And we, in practice, calculate what is the detectable X-ray emission by integrating along the line of sight of SMILL. And in this way, we produce the 2D maps from the MHD simulation, which then we put through the SXI simulator to, which contains the response of the instrument, of the CCDs and so on. And we produce maps like is shown at the center of the slide, count maps. And there are numerous there is a large number of people that are working on these images in order to, first of all, simulate with different conditions of the solar wind, as well as identify what are the best techniques for extracting the magnetopause position, the morphology of the cusps, and so on from these images. And now I turn to the other instrument on board SMILL. The UVI, the ultraviolet imager, is a 4-mirror reflecting telescope that monitors the complete auroral oval in the northern hemisphere at high spatial and temporal resolution, 150 kilometers resolution, maybe better, and temporal resolution of like 1 minute. The UV band pass is quite narrow because we want to avoid as much as possible contamination from day glow, and is achieved by coating the optic and the detector surfaces appropriately. And the detector is essentially an image intensifier. Now, you see the inner workings of the camera in the bottom right-hand diagram. And the camera is the responsibility of Canada, and the PI is Eric Donovan of the University of Calgary. The coatings of the mirrors the coatings are due to the University of Liège in Belgium. And the electronics are Chinese responsibility. And on the left, you see at the bottom a picture of the engineering model of the UVI electronics, and at the top is the breadboard of the optics of the camera. And UVI will return images similar to those that the image satellite returned. And you see some examples here. But of course, in the case of SMILE, we will have full coverage of the whole oval throughout the 40 hours of observations. And as for the SXI, also in the case of the UVI, there are people modeling the aurora with an end-to-end simulator. And you see an example here. And in particular, what people are concerned and studying in great detail is the way of excluding day glow from the images that we will gather. And finally, there is the in situ instrument package, which is the responsibility of China, and is made up by the light ion analyzer, LIA, and the magnetometer. Now, the LIA, you see a picture at the top left of the engineering model of the LIA with the sensor and the electronics, is a top hat analyzer for protons and alpha particles. It's going to measure density, velocity, temperature in the energy range of 50 eV to 20 keV. So it's appropriate to both solar wind and magnetosheath. It's got the two sensors are mounted on the platform, which you'll see in a moment in the next diagram. And so there are two sensors so that we get a full field of view of 360 degrees in azimuth, 90 degrees in elevation. The magnetometer is of the flux gate type, measures strength and direction of the magnetic field, incorporates two sensors, and they are mounted on a 3-meter long boom. And you see there at the bottom right-hand corner, a test, a deployment test of the boom carried out in China. So here we see the SMILE spacecraft in its launch configuration. And at the bottom, there is the propulsion module, which is made up or incorporates 4 big tanks of fuel that have to push SMILE up to its highly elliptical orbit. Above it is the service module, that cube type of structure. And at the top of the service module is the payload module. And this is practically an interface plate on which SXI and UVI are mounted. And the shares of responsibility are as follows. ESA provides this payload module, this interface plate, and as well as the launcher and the integration and testing facilities for the spacecraft in Holland. And ESA member states and Canada provide the Western instruments, the imagers. The Chinese Academy of Sciences provides the propulsion module, the surface module, the prime contractor for the spacecraft, and mission operations, with some contribution from ESA, and of course the Chinese instruments. Here we see some images of tests that have been carried out on the structural model of the spacecraft in China. And here we see very clearly the propulsion module, and above it the service module with the solar panel folded in as a launch configuration. That was a mass property test being carried out. Here we have an image of the vibration test and acoustic test as well. Talking about orbit and operations, the baseline is a perigee of 5,000 kilometers altitude and an apogee of 120,000. The period is 51 hours, of which 40 are operational for SXI and UVI. The launch is expected, as I said, at the end of 24. And at the moment, there are two possibilities for the launchers, although Vega C is defined as the baseline. And in that case, SMILE would be single passenger and would go to an inclination of 73 degrees. Alternatively, there is the possibility of going on Ariane 6, but in this case, it would be a dual launch. So SMILE would be like a piggyback passenger, probably to accompany a Earth observation satellite that are very often launched. And it would finish up in a sun-synchronous orbit, probably pretty low altitude to start with, and then eventually be pushed up to its very elliptical one, but after probably sitting in this preliminary orbit for some weeks or some months. Both launches would be from Kourou, and the selection of launcher is going to be taken at the time of the mission critical design review in 22. And the ground stations are expected to be Troll in Antarctica, is the baseline by ESA, and support will come from Sanya in China. Now, a launch at the end of 24 is actually not bad, although is delayed with respect to what we were expecting to start with for SMILE. And the reason is that the latest forecast for solar cycle 25, in which we are now starting, is that the maximum will be around July 25. So that's just about the time when SMILE will start being operational. So we have, we can expect a good number of strong solar events happening that would be interesting targets for SMILE. I want to mention the fact that there are several working groups for SMILE that are working to prepare for the mission, planning for it. So to start with, we have a science operation working group and a data format working group. They are strictly related to the way that SMILE will be operated. And so there are discussions ongoing on the protocols of exchanging commands between the PI instruments, PI institutes, and China that are going to control it. They have the control center for the satellite, and the data formats discussing the formats in which the data will be produced and the best way to be given out to the users, how to archive the data, and so on. Then we have an in situ working group that looks after the calibrations and the operations of the in situ instruments, and a very active modeling working group that, as I have described, where people are simulating the kind of images from SXI that we can expect to get for different conditions of the solar wind, as well as determining, devising, developing techniques to analyze the images and extract as much information as possible from them. And there is also a very active and important ground-based and additional science working group, which is looking after the synergy that there will be between SMILE data and observations with facilities measuring the conditions on the ground of, conditions of the solar wind impact on the Earth. And also, this working group is looking after the synergies with other spacecraft, the magnetospheric study spacecraft that will be flying at the same time as SMILE, so that we can combine data observation to make the most of the data returned. And then finally, last but not least, is the outreach working group, which is promoting the mission involving more public engagement in it, especially being a visual mission. It's got lots of potential for that. And I would say you are welcome to express interest in these working groups, and let me know if you want to join. We are certainly open to more interested parties. I always like to show this picture. We have consortium meetings every 6 months, and normally we have one in China and one in Western countries. And this was the last one we had in China, in Xi'an, in May 2019. There was one more face-to-face in the October, and then since then, we only had virtual meetings. But this is a nice picture showing many happy people working on SMILE. And also it was a very nice trip to China, to Xi'an, because we had the opportunity of seeing the terracotta warriors that we were, of course, invited to go and visit. This is my last slide to conclude on the impact that SMILE is going to have. From an X-ray astronomer point of view, as I am by background, I am really grateful that X-rays from the magnetosphere have gone from being an unwanted nuisance for X-ray astronomers looking at cosmic sources to a real diagnostic tool for the relationships between the sun and the Earth. And what's interesting is that SMILE, in this sense, joins up diverse science communities of astronomers, planetary scientists, magnetospheric physicists, in a very interesting collaboration in terms of also of how we approach the data, of how we interpret things. Very makes this collaboration makes life very interesting on this project. Now, SMILE basically will provide science input to the studies of space weather. It certainly is not an operational space weather satellite, but it will provide the remote sensing data that are necessary in order to validate the models, the global models that have been developed in trying to represent the interaction solar wind magnetosphere. As I said, it's got a strong potential for outreach because it's a visual mission, and the images, the movies will captivate the public into a science that of the Earth's magnetic field that has been invisible so far, and it will make it visible. And the cooperation with China is an aspect that is also rewarding. SMILE is an exemplar of how we can work together, and of course builds on the ESA experience on Double Star already. And I'll stop here. Thank you for listening, and let me have your questions.
Thank you very much, Graziella. That was fantastic.
Okay. Tell me what I should do now. Shall I leave the slide on? Shall I stop sharing? What should I do?
I think if you leave the slide up, because people might ask questions that depend on slides.
Yeah.
And we've got a couple of questions in the chat already. We've got one from Mike Lockwood, and he asks, do the mission intervals and orbits of the other soft X-ray missions give any opportunities for tomography of 3D structures?
Well, that's very interesting. In fact, I would say if Storm flies when it should fly, 25, 26, it's under study, so it will take some years to develop. But we have certainly talked that already with them that tomography would be a great thing to do. And of course, there are the other ones as well. I haven't particularly discussed with the Japanese and the Chinese, but I'm sure that if there is something flying at the same time, it makes very much sense that we collaborate. And as I said, we have already this ground-based and additional science working group that is aimed at that, to look at the synergy with other missions flying. So it's certainly in our mind.
Excellent. And I guess I have a follow-up question to Mike's question, which is I was wondering, do you have a feel for whether or not the missions being up at the same time will enable kind of interhemispheric comparisons at all? Is there anything that's going to be observing the southern hemisphere while SMILL is observing the north, for example?
I'm not now. I don't remember exactly what the storm orbit is, but that probably could give us an opportunity for sure. We are open to possibilities. Yeah, that would be a great thing. Yeah.
And we've got a question from Jasmine Kaysandu. So given their capabilities, do you think that soft X-ray images will become a routine instrument on future space missions?
Yes, that's what I want to see happening, and I have been promoting for many years. Like, for instance, going to the outer planets. It makes absolute sense to have an X-ray imager on board. X-rays have got to get on par with UV imaging, because they explore the higher energy condition, different processes. And we see what we can do right now with the remote observations of Jupiter, having Juno in situ and observing with Chandra and XMM. But we are limited by the fact that we cannot have continuous observations, that we are far away, so the sensitivity is low. So it makes very much sense in making in situ X-ray observations.
Excellent. And Jasmine also asks, what are the main challenges of observing soft X-rays in other planetary environments compared to Earth?
Well, okay, for instance, in the case of Jupiter, one has always got to worry about radiation, the strong radiation field, energetic particles and so on that can affect the behavior of the detectors. That's the thing that comes to mind. You wonder, what are the difficulties? Well, you have to get there, of course, so you have to have a fairly relatively small instrument, but with good sensitivity. So you need to study precisely, what kind of effective area you want to have and so on. But it's certainly feasible, and it's demonstrated now that we can produce X-ray imagers that are valid and sensitive enough, not having huge observatories like XMM and Chandra. With this micropore optic technique, we can have a very large field of view, which we need if we want to have a good view of the planets, and with a limited amount of resources really on board. Yeah, so.
Excellent, thank you. We have a question from Martin Archer. So he says, other first images, such as the first radio image of a black hole, the people who took those images put a lot of effort into processing to make them visually striking as well as scientifically interesting, so that they could be widely shared on social media and kind of things like that. Is that something that the outreach group for SMILL has thought about at all?
That's a good point. Not that I know about, but I am certainly interested in trying to, as I said, get out as much as possible from them, and in enhancing the visibility of the various characters in the images. So I certainly appreciate any suggestion, any help in disentangling the various morphological entity in these images. We have been working, but this was on different type of images, but it should be possible to do it with this. In fact, it's something that I have really considered. We have been using machine learning on other planetary images to try and sharpen up the resolution. So that's one possibility that we could try, but we haven't done that yet. Good
Cool,
point,
thank you.
good suggestion. And if you have a suggestion on techniques, please send them my way.
Excellent stuff. So I think that is all of the questions that have been posed in the chat. Mike Lockwood notes that the imager that you mentioned that's going on the moon should give opportunities to see both cusps simultaneously at half moons. So that's a good point from him. And Jenny Carter notes that Storm will be at 30 RE and will have a 90 degrees inclined orbit. So thank you very much.
Okay, so that means we should be able, it will go over both poles, right? Yeah,
yeah,
good.
I think so.
Good.
Brilliant. Okay, so I'm going to stop the recording now, but I'd just like to thank Graziella for her time and her excellent talk one more time. And we'll see you at the next MIST seminar.
Indeed.